Welcome to Spring LIB.
Alrighty, so we got a river. We have the velocity of the water relative to the shore equal to 0.5 meters per second. So just a little known there that I want to keep in the problem. And let's just start out right away. Let's just dive right into this problem. I think that's the best way to go ahead with the relative velocity problem. So first, let's get the velocity of the student relative to the shore. We can go ahead and find that as so relative of the person, P for person, relative to the shore. And that's going to be equal to the velocity of the person relative to the water plus the velocity of the water relative to the shore. It's like a chain. When you're doing relative velocity problems, you kind of just chain it all together. It's the velocity of the person relative to the shore. Well, no problem. You just got to determine the velocity of the person relative to the water, and then add to that the velocity of the water relative to the shore. And that's how you can get that relative velocities. So if we go ahead and we punch in for this, we're looking at 11.2 minus 0.5, and that gives us 0.7 meters per second. So we got that, and now we calculate the time it takes to end the upstream swimming trip, and we'll just do that using the information that we just found. So we have d divided by the magnitude of the velocity that we just found. So it's the velocity of the person relative to the shore, and little bars here to represent magnitude. And we know the distance is 1,000 meters. So 1,000 meters. And we divide that by the 0.7 meters per second that we just got. And when you do this, you'll be left with your time, which is 1,429 seconds. 1,429 seconds. Excellent. Now, what about for the downstream trip? Honestly, if we're curious about that, that was for the upstream swimming trip. What about for the downstream? This is little one here, T1. So let's just follow a similar method here. So we'll use the velocity of the person relative to the shore, and use the same kind of deal, the velocity of the person relative to the water plus velocity of the water relative to the shore. Go ahead, punch these in, and you get negative 1.2 this time around, and we have a negative 0.5 for the velocity of the water relative to the shore. And this gives us a negative 1.7 meters per second. All right, so now let's go ahead and try to figure out the time for the total trip. Before that, though, we'll just find T2 real quick first. Same method that we just did to find T1, distance divided by velocity of the person relative to the shore in the second case. And that's going to be 1,000 meters divided by 1.7 meters per second. And we're looking at 588 seconds. All right, and we can find the total time for the whole trip. T equals to T1 plus T2. All right, and that's just going to be 1429 seconds plus the 588 seconds. And when you add those up, you're looking at 2017 seconds for the total time to do the swim. All right. Now, when the student swims in still water, keep in mind what happens in still water. So that's part B. Let's just write this up like this. In still water, the velocity of the water with respect to the surface equals 0. Real easy swimming environment. So what we're going to do is we're going to use the same kind of method again. So velocity of the person with respect to the water, and that's equal to the velocity. Oh, I'm sorry. I meant to say is velocity of the person relative to the shore. But then this would then be equal to the velocity of the person relative to the water plus the velocity of the water relative to the shore, but that's 0 as we just found. So you set that equal to 0 there, and this is equal to 1.2 meters per second. So the time it takes to finish the whole trip, let's do then t equal to this 2 times 1,000 because it does the whole trip, and you divide it by the velocity 1.2 because it's still water, and we're looking at 1,667 seconds for still water. And see, they're asking us about the, why is it just intuitively, like what's the difficulty with swimming in current? And it's a good point. Swimming against the current takes more time than swimming with the current. And that's just a simple aspect of force, because you have a force that's pushing against you and essentially just making it more difficult for you to swim. It's the equivalent if you were to try to walk in the opposite direction of a one of those walkways at the airport, like those motorized walkways that assist you in walking the longer distances. If you were to go against that, it'd be much more difficult to walk. So kind of similar situation here.